I start? Okay. I'm going to talk about my research paper about work-causing phenomena and the refined BPS invariants. So basically, I'm considering the type 2 superstring compactification on some Calabrial space, and the low energy effective action will be n equals to supersymmetric gauge theory. And we also want to consider some substate called BPS state. This state satisfies a condition that the central charge of the BPS state and saturate their bond so that equals to mass. 那这个 and then this BPS state can be graded. The Hilbert space of the BPS state can be graded by their charges and can also be graded by their spin content. And the goal of my research is try to understand the spectrum and some invariants encode their physical informations. So this spin content can also be understood as M theory. So if we compactify M theory on the same Calabrial space, then we get a 5-dimensional field theory, and their little group will be SU2L plus SU2R, and their quantum number is this spin of this 5-dimensional BPS particles. So the Hilbert space can be composed as the charges and the spins, and come back to the 4 dimensionals. The left spin will become to the spin of the spin content of the 4-dimensional BPS particles. So we want to study some invariants called the BPS index. This is the trace over all Hilbert spaces and insert fermionic particle operators. This is also called Witten index. It basically is the number of bosonic states minus the number of fermionic states. But we also want to this index basically is only contains the charge information. So we introduce another index called the refined index, and this Y will encode some basic information about the spin content. So this the type 2B contains some degrades, and when they come wrapping on some holomorphic submanifold in the Calabrial threefold, this will generate some BPS particle in 4 dimensions. So given a BPS state in a series, then we can define the phase of these central charges, and some semi-stable objects will satisfy the following conditions called semi-stabilities. If some state may composite by some particles, and some composite, their phase should be less than their original. And as we vary some parameters like Coulomb branches, and the central charges is depend on these parameters. So it may, at some point in the modular space, it may violate these stability conditions. So, for example, if 2 states gamma 1 and gamma 2 compose another state called gamma 1 and gamma 2, and this is the central charge. And if we vary the parameters, this central charge may parallel. And we vary further this gamma 1 is the subparticle of gamma 1 is gamma 2, and so in this situation, the state may become unstable.
Sorry, do you mind not to talk directly into the microphone?
Okay.
It's
Okay.
too loud.
Okay. And the space is the modular space of different configurations. It's conjectured by Douglas, and in some cases, rigorously proved by some mathematicians. And in this modular space, as we see before, when the central charge powder means that their phase is the same. So in this case, this is proportional to real numbers, and the sectors between these walls is called chambers. That's the name where those come from. So basically, the BPS index is invariant in the chambers, and as we close the wall, then the BPS index may change. So they need more. They use statistical mechanics to determine the jump of BPS states in the simplest examples. And in general case, Conservation and Sagelman, they state that if for every state we give them a quantum dilogarithm, and this state has a order in the central charge, and we plot them in some order. In this case, it's anti-clockwise orders. Then it is a constant group by ranking. So we can use this invariance to show out some before closing the wall and after closing the wall. This invariance should be the same, and then you can use this formula to compute the partition function and the index in each chamber. So we take an example. It's called a result formula. Basically, it's a non-compact Laplace threefold, and this is basically a two-sphere, and the fiber was some run two bundles over it. So, and the effective theory is U1 gauge theory, and the BPS state is the D6 wrapping all the non-compact space, and the D2 brand wrap only the two sphere, and the D0 brand can bond them. So, as we change the parameter, and in this case we change the B field. So the BPS state will change. And Jeffrey Moore used this gamma 1, gamma 2. Gamma 1 is some only D6 branch charges, and gamma 2 is D2, D0 bound states. And they may form a two bound states. The central charge is given by this and this, and they aligned in this phase. So the wall is determined by this equation. So basically, this is the wall and chamber structure in modular space, and around this 90 degrees is called core chambers, and in this chambers only pure D6 branch states and the D0 D2 bound states, and as we increase the B field, they may form a D6 D2 D0 bound states, and we denote the invariance as this. As we increase B field, they will gradually accumulate to this phase. So by other method, we can compute the invariance in the core chambers and use the work causing formula to compute the other chambers. So we can compute the rank 1 means only one D6 brand bound with D2, D0, and the partition function is this. And then use Walker's formula, we can also compute the 2D6 brand bound state, and the partition function is like this. And this one looks just like the square of the rank 1 plus some two-centered bound state corrections.
1 more minute. 1 minute.
Yeah. So basically, for general non-contact LBLs, the computation is very difficult in this method. So I'm trying to study the method series to try to further understand this BPS spectrum. Thank you.
Thank you. We can have some short questions. Yes.
What's the quiver for the counting?
It's basically it's only basically there are 3 vertices, D0 and the D2 and the arrow between them, and another D6 framing between this D0 and the D2.
How many arrows?
It depends on which chambers. As we change the parameter, there's some mutation of the figures. So in the core chamber, there's no framing because there's no D6, D2 there downstairs. And after we
Draw it?
sorry.
You draw it.
Okay.
Probably easier.
Or maybe we can discuss later because we'll over time.
All right. Let's thank Wang Jianxun again. The next talk will be given by Li Zhaorong.